No. You don't have anything else to do? Don't play with my phone. All right. Hello?
Hello.
Hello. You're out there?
Yes.
Good. Anybody else? Is there anybody out there?
Yes, we are here.
Okay, great. I'm actually kind of ready. You saw what I did? I used the Moodle instead of using. I wonder if this is going to work multiple times. I made it so it should be at the same link. I made it that the same link should work multiple times. But I don't see anybody. Can somebody turn on their, I need somebody to put on their video. I can't talk to an empty room. Thank you. Thank you. And then I get to learn your names. Ariel. Well, I like your back. You've got like a background that looks like the Northern Lights. I muted you. Wait a second. Can you unmute yourself?
You can change background. Yeah.
You can change the background? That's pretty cool. You look like you're in Star Wars, in Star Trek, the original series. Hello.
Hi.
Oh, you're Barenbaum. But you're why am I not? Okay, anyway, so let's start. First of all, is Yitz here? Yitz asked me, Yitz, are you there? No. Well, he asked me that you guys might have questions with the homework. Let me start with that. Are there any questions on the homework? Okay, I see a chat. No questions on the homework?
Yeah, I have a question on the homework.
Yeah.
Okay. Let me, yeah, so go ahead. While you're doing this, I'm going to look at the homework. I just, by the way, put up homework number 2, but you guys are not prepared to do number 3, actually. We skipped number 1. Number 3 I put up, and you don't have to do it because you don't know enough to do it. But yeah, question on homework 2, which is the first one you have to do.
I was trying to do it, so I just can't quite figure out how to do it.
Well, which question? You've got to specify something.
Okay, well, so the first part of 1, you managed. Then even like part 2 of 1, I had a lot of trouble.
It says like, so the question is, what value will be in V0? You guys, if you're with me, you should look at the homework assignment number 2. What value will be in V0 by the end of the program as a function of n? Explain. So, I mean, it should be very easy, no? You first of all, the second line of the program you put into T1, whatever n is, and then.
Yeah, but
What? Yeah.
I'm having trouble figuring out how do we follow the program if we don't know what n actually is?
Well, I don't see that the branch relates. Does it relate to n? Oh yeah, 2. Yeah. So if you don't know what n is, so the way you do that in general is you assume it's some number. Say, okay, let's say n is first you started with an average number like 2. Later you might try also 0. See what happens if you get 0. And you might also see what if it's a negative number. That might also be.
No, but doesn't it say that n is a positive number in hexadecimals? So everything is
yeah.
positive.
So there you go. It's a positive number in hexadecimal, right? So therefore, you don't have to try negative, but you do have to try 0 maybe. Let's assume it's 2. So
what I did, the problem that I got into is that like I now did 2 options when n is bigger than or smaller than 2, and when n is equal to 2 or bigger. So those are the 2 options, but I feel like I got into an infinite loop because at some point in the SRL, when you don't branch, you divide by 2. and then you have n divided by 2, then n can either be 2, can either be 1 or 0. So you have either 1, a half, or 0, and then you
First of
go
all, you're
into
never
the
going to
loop
get a half.
again.
Obviously, you're never going to get a half, right? 3 divided by 2 is going to be 1.
It's just going to throw out that last bit, right?
Yeah, because that
It's
last
just
bit,
removing.
that last bit sort of drops off into the. Here, actually, I have a picture here.
Yeah, it will become 1. I understand, because it shifts to the right. It's a shift to the right, right?
Yeah, shift right logical. So look here. Let me
So
just
it's divided by 2, but it will become a 1, so you can't have in half.
wait a second. Here. Here. I drew some pictures for another class. You see that?
Yes.
So that's the first. What you see on over here is a shift left logical going. Notice that they starts off with 2 1s on the left. And then they shift over the space and 0 and drops off.
I can't hear you anymore.
Ah, sorry. You see it now? And you hear me now?
Yes,
Hello?
I can hear you. But this
Okay.
is shift left,
This is
right?
shift right logically. So you see it's multiplying by 2. It starts off as being 3 and then goes up to 6 and the 0 drops off and then the goes again, it goes up to 12 and the 0 drops off. Here is a shift right arithmetic. This is not shift right logical, it's arithmetic. The only difference is that the fill, well, what the fill is, but look at this, first of all, look at it, what it does. When I look at it again, it's, well, it's some large negative value, and or some negative value, and then I shift to the right. Now, shift right means that I have to fill in something over here. Now, if I would logical, the filling in of that
Something is blocking the microphone.
Now you hear me?
Yes.
Yes.
So you see the shift right logical? And shift right, sorry. This is a shift right arithmetic, which means that when it shifts to the right, well, let's start with shift right logical. Shift right logical, when it shifts to the right, it would fill in a 0. But this is a shift right arithmetic, so it's going to fill in whatever was the sign before it did the shift. So in this case, since it's a negative number, the value on the right, the value on the left will be a 1 instead of a 0. But you're not doing that in this case. This is a shift right logical, so it's going to be a 0.
So it'll always be a 0. Yeah.
So it'll always be a 0 no matter what the number is. So if let's go back.
So the answer should be something like, if n is bigger than 2, then register v0 is 0. If n is like 2 or 1, then v0 is. Should the answer be like that?
Well, let's see. Let me start off. Let me look at it together with you.
Okay.
So this says, let me just screen capture. Screen share here. Share. Okay, so we put 0 into T0, we put n into T1. Fine. So now we say shift left logical. So that means it's going to the left, it's getting multiplied. By how much? By 2.
2.
And what value is being multiplied by 2?
No, wait. Does SLTI not stand for set if 2 less than n?
Oh, I'm sorry. You're right. I got confused. I thought it was a shift. You're right. Sorry. Never mind. My mistake. Thank you very much. Shift is going to set less than. It's right. It's an SLT is a set less than. So it's going to set T to 1 if T1 is less than 2. So if it's exactly 2, it's going to remain 0. sorry, it
What
says,
what I understood on the internet is that it's the other way around. That if 2 is less than a T1, and that's what I just found because I'd never heard of SLTI, so I looked it up. And what
no,
I understand,
well, I would be very surprised if you're right. Let's see, but I could be surprised. Just a second.
What did he say?
Let me just check before I repeat what he says. I'm just going to check.
yeah, just make sure because otherwise
Yes.
my whole program doesn't make sense.
Yeah.
What I look at the internet, if it's smaller than 2, it becomes 0. If it's bigger than 2, it becomes 1.
Yeah, but the question is which one? Just a second.
The
just
ST2.
wait a second. Wait a second. Just wait a second. And I'll share you my screen. Okay. Zoom. I got this is one thing I find annoying about Zoom. If you do a share screen, you have to do a new share every time you.
No. We see it. We see it.
Oh, you see it?
You're still in the
Yeah.
same window, so you're still in the
Ah,
Chrome window, so the whole Chrome is shared.
okay. Oh, excellent. So, this is SLT and SLTI. They should basically work the same. And what it says is the syntax is SLT and then D, S, and T. So when is D going to be equal to 1? Look at your operation. When is D going to equal to 1? When the left one, S, is less than the right one. True? That's what it says here. Agreed? I need somebody
Yes,
to say.
so it is
Yes.
set.
Now let's look over here at the
Yeah.
SLTI. And let's see if it's the same. It should be the same. It says if S is less than the immediate, well, that's the same. If the left one is less than the immediate value, then T is 1. So it's the same. So therefore, we're always checking if the
It's the same,
one,
except one's comparing it to a register and one's comparing it to an actual number.
yes, exactly. That's the only difference. This SLTI is comparing to an immediate number, to a number there written in the code. And SLT is just comparing to 2 registers. But it's always the first one. If the first one is less than the second one, then the first register is 1.
Okay, so in words, what we're doing.
So let's
is
go back. Wait, let's
set
go back
if
to the
n is
Targil.
less than 2.
So here, this means that T2 will be 1 if T1, which is 0, no, which is 2 in our case, is less than 2.
T1 is n.
So is 2 less than 2?
Yes. No.
No,
It's equal.
2. Those are your 2 choices, yes or no. If 2 is not less
equal.
than 2, it's equal. So therefore, it's not less. So
Well, it
therefore, this will be
depends
0.
It depends
So
what
it's
n
0.
is.
What?
Depends what
That
n
makes
is.
sense.
If n is 2, I have to think about,
Yeah,
let's say n is 2. N is 2. So 2 is not less than 2. So this T2 will be 0. If T2 is not equal to 0, then finish. Well, it is equal to 0. So we're not going to finish. So we're not going to go to finish. So we're going to go to this line. And we're going to take T1 and we're going to make it be whatever T1 used to be, but with a right logical shift, which means it's all the bits are moving to the right, which means and I'm putting in a 0 there. So, well, that didn't matter because this is a positive number anyway, but we're putting in a 0
So it'll be
there.
a 4.
It'll do division by 2 without a remainder. So if it was, what was T1 before? It was 2.
2.
Now it's going to be 1.
Wait, shift left, isn't everything shifting to the left? Doesn't it
No, this is an
add
R.
a
It's
0?
an R. It's an R. Shift to
Oh,
right.
shift right. Yeah, okay.
Shift SRL. Shift right logical. So it's going this way. So if it was 2, if it was 2 here, it's now going to be a 1, and this will all be zeros. So it went down to a 1. And now, what am I doing? I'm taking the T0, which was 0, and incrementing it by 1. Well, that sounds like it's a counter. I'm adding 1 to it. So it's just, so it sounds to me like T0 is a counter. Now I jump back up and I check again. Is 1, T1, which is now only 1, is it less than 2? Yes, it is less than 2. So T2 will be 1 is 1 not equal to 0? Yes, it is not equal to 0. So go to the finish, and then do what? Then put T0, which is my counter, into V0. So basically, if I could define what it's doing in terms of n. I would just say it's counting the number of times. Yeah, this is the answer. It's counting the number of times I can divide n by 2 without getting 1. In other words.
But don't you? They're specifically asking the value of V0, but for the number of n that can change.
Yeah, in turn as a function of n.
So
Yeah,
what
obviously
I'm saying
V0 will be different every time.
V0 will, if n is 2, then V0 will be 1. If n is 4, then it'll be, so it's actually the power minus 1, whatever. It's the log. It's log base 2. No, if you want to say it in mathematics. It's how much. It's the power. It's how much the power is. You understand what I'm saying? If it's 16, if the number is 17, then it's 17 divided by 2 is 8. Divided by 2 is 4. Divided by 2 is 2. Divided by 2 is 1, and it's going to end. So it's going to be 4. So it sounds to me like the answer is it's the power of 2. It's log n, log base. It's log n base log 2n. That's the answer, right? You see what I'm saying by log?
Yes. Yes, I
It's
see.
the power that I can. It's how many times I can put 2 into that number. You can say it like that. It's the same thing. How many times I can divide that number by 2?
Wait,
before
you're saying it's a log? It's a log function?
Well, I'm not so good at math, but isn't log telling me the power, how many times I can put 2 into it? Doesn't matter. Forget about
Yes.
log. I think that's what it is.
Meaning it's counting how many times you can shift left.
Yes, how many
shift
times you can shift left before reaching 1? Well, but if we understand intuitively what that means, I mean, we can think, well, who cares? It's telling
Right,
you.
it kind of sounds very logarithmic.
It sounds very logarithmic. So that's it. Nothing complicated about this, except that you had to know what SLT is and SRL is. In this case, if it was SRL, well, there is no shift right, or SRA, it would be the same. Doesn't really matter because it's a positive number, so always it's going to put a 0 anyway. All right, does that help you, Yitz?
Yes, it does.
Now, this would, if you would write the programs in the Mavada, in the lab, you obviously would be more, I mean, we don't have a lab, but we had a lab, and you did the programs, you'd get more familiar with the language. All right, I don't know. I think, first of all, you can also just, I mean, I don't say this is cheating, but at a certain point, if you can't figure it out, then you can always just cut and paste this into the compiler and run it. True?
No, but we don't know what n is.
Put in a number.
You can define.
Put in a number and see what happens.
And the compiler, you'd have to write it in hex, or could you write it in
No,
binary?
in the compiler, I could write it just like this, 5. But if I want to write in hex, I need to specify 0x, and then I can write A.
Can you do it in binary?
I don't know. I'm not sure how to do it in binary.
Can I ask you something about question 2?
Yeah, and then we should get to some new material. But yes, go ahead.
Okay, so question 2, number 2, where it's I thought it was a JR command. Is that correct?
I'm not. First of all, I don't remember all the answers to all these questions, and even if I did, I wouldn't tell you.
It's
I shouldn't tell you.
First, it just didn't make sense because the first 6 if is 0.
Well, first
and
of
then
all,
the
I see that
rest
the first thing I see is
so that should be a GR command. But then the after 5 digits is 0, which is fine. That's the R.
wait. Let me talk. Let me talk.
Okay, sorry.
The first 6 digits are 0. So that means it's an
Yeah.
R type. Agreed?
Mm-hmm.
So it's an R type. To know what command is, I got to look over here for the function. And I look over here and I see its value
8.
1, 2, 4, 8. So then I go, where was that page? I don't know. I had something. Yeah, MIPS. Oh, this doesn't tell me, but I can go and I can say MIPS green card. It will not get you entrance to the United States, but there's this kind of green card. But here it is in green, you see, but it can also be in white. And how do I do that? Oh, why is this thing here? I have to remember where is the best place to view this green card. Maybe here. There we go. Sign up to download. Oh, everybody's giving me a hard time. Anyway, there's a chart. There's a chart that shows you what the commands are. 8. Oh, I happen to see right there. 8. No, but that's for the opcode. I need that the hex will be 8. I need that the function will be 8. I just have to go in this table here and find the opcode, which is 0,
Maybe
and the
found what
function
you
code, which is 8.
needed.
I can't believe there's more than one.
Here, is this what you needed? I'll put it in the chat.
I can actually, you can go, oh, you put it in the chat?
Yeah, there. It's on page 2, I think. I found something. Maybe that is what you were looking for.
Well, I mean, the main thing is I want to show you how to find such a thing. Not, I don't need to show you the answer. The question is, how does one solve such a question? And you need a table like this. I think there's one on Moodle, actually. If I go to Moodle and I go to the course, oh, I don't know if it lets me.
Wait, yeah, can you use the PDF that he just posted on the chat?
Yeah, where is the chat? I don't see the chat now. Oh, there, chat. Why don't I see the chat? Control Alt H. What does Alt H do? Doesn't do anything. Why don't I don't see the chat. That's my only problem. Maybe it's a different window. No. I don't see the chat for some reason. It tells me chat is Alt H, and I press Alt H and nothing happens. Alt. Let me go here. You guys see my Moodle, right?
Yeah.
Yes.
So if I go here, there should be
It's probably on the other one. There are
No.
2 pages of
here
Mivne.
it says Pekudot Assembler. Choveret Ezra Mivchan. This is actually the thing you get for the Mivchan. So it's actually worth looking at. Here we go. And it says opcode and function. So I'm just going to scroll down until I see 8. You see that 0, 21? I want to see 0.
We can't see it.
We're on the
You
wrong
can't see
window.
it, it's frozen.
Oh, it's frozen. Okay, sorry.
No, it's in a different window, I think.
Yeah, it's in a different
You need to
window.
share your full screen.
New share. Oh, you can do share full screen? I don't know how to do that.
Yeah, just don't select any window. Just click on the top left, just click screen.
Oh, screen, yeah. Okay, now you see?
Yes.
Oh, now I
Yes.
see the chat. Somebody sent. Okay, well, I'm closing it. So here's the document that you're supposed to get for the Mifchan. We always wonder if we have to translate it. I say we don't really have to translate it because it's all English except for like the titles. So here we have to go and look for 8. Oh, 08. See that? 08 JR, jump register. Jump to address stored in register RS. PC equals RS. That's something else. But everyone sees what I'm talking about?
Yeah.
So if I go
Yes.
to the homework, back to the homework, if I see it's 0 and 8, it must be a JR. If the only question is what is the operation, then that's the operation. But they may also want to know, well, it's a JR, and this is going to be the jump address. This is the, no, these are the register. Well, we have to now
No,
figure
that
out
was
what.
my question. Why are these ones there? Isn't this supposed to be 0 and only the first 5 bits are supposed to
So
be
let's go back.
the thing?
Where was that? Here? No, not here. So I'm saying, what's the format of this command? Well, what is JR? What type is it? It's a good question. Well, what did we say about the JR? What did we say about the
Probably-
JR? It is
probably
it's a 08, right?
Yeah.
It's a 08. So which type is it?
R.
Gotta be R, because it's 0 over here and it's 8 over here. The shift amount is going to be irrelevant for a jump. It's a jump to a register. So it's going to be one of these. One of these will be the register that I'm jumping to. Which one? Well,
the RS, right?
could be. Oh, that's what it said, right? It said RS. So it's the RS. So that should be the one right after, that should be bits 25 to 21, which is right after the top. So it sounds like it's jumping to address 0. So what are those ones there? They should be ignored. They should be irrelevant.
The ones are just ignored. They can be anything. It doesn't matter. It shouldn't be just 0.
No, it'll be ignored. It's not going to even look at them. Why should it look
So
at them?
this is one. So that is one of the that's one of the functions that won't do anything because it's just jumping to itself.
Depends where this function is, where this command is sitting. If it's sitting
Well,
at
it's a-
0. First of all, are you allowed to jump to address 0?
No, isn't that reserved for the OS?
The operating system. It is reserved for the operating system. It shouldn't allow you to do it. Kind of a weird
So that
question.
should be one of them that you can't go to. It wouldn't do anything because it would try to and it would crash.
Right. It should crash actually. Unless they specify something in the question. Which of the following commands which are stored in address 0? So they're in address 0, and so you're jumping to address 0. Do not do anything. That is, they do not cause any changes in any registers or data memory, and do not change the order of execution of the instructions. Well, this is a tricky question. This is a tricky question because it's going to be an infinite loop, right?
Yeah, but regardless, won't it not do it the first time? Because even if it's already there, first of all, how could it be there? Isn't that reserved for the operating
Right.
system? Like, how could it?
So first of all, the fact that it's reserved for the operating system is really in the simulator. You could theoretically have a MIPS chip with no operating system. The operating system is not inherent to the architecture. You see what I mean? The operating system is a program in the end. It's just a program that somebody put on it. So the chip itself doesn't care. So actually, from this question, he's talking, it's pure architecture question. See what I mean? He's not interested in whether, you're right, that's reserved for the operating system in the way we're, in a normal use of the MIPS chip. But I could buy a chip from the factory and not put an operating system on it, just like I can buy a computer and not put an operating system on it. See what I mean? So in this question, we're not assuming anything about the operating system. So therefore, it would be, valid. Therefore, it would be valid to jump to this address. But it would be an infinite loop. So it's a little bit tricky because they do not cause any change in the register. No, it doesn't cause any change in the register. Or data memory. It doesn't change data memory. Do not change the order of execution of the instructions. Well, that's kind of depends. I mean, that's hard to answer because it's never going to get anywhere. So it doesn't change the order, but it doesn't allow you to do any other instructions.
Wait, what was the whole PC changing? The PC was changing?
We never discussed the JR in class. We discussed a jump and how a jump calculates the address, and we discussed how a branch calculates the address. A JR is not a jump command, even though it has the word jump in it. It's not a J type, it's an R type. You see what I mean? Actually,
but it was changing, the function seemed to be changing the PC.
Doesn't it jump to the
No.
address of the register?
Yes, and the address of the register is 0, we decided.
Yeah.
Wait, I want to look, so it jumps to address 0. Where was that thing? I wanted to go back to the, all right, let me go to here, and let's do Hoveret, not the thing for the test, the other thing that I had. Here it is. No, that's the same thing. Wait a second. Is this what I want? No, I don't want this one. I want the other one. What's this? Yeah, this is the MIPS instruction set. And now if I go down, that's a jump and link. Where is jump register? Oh, is there a jump? Should be in alphabetical order.
This in the Moodle?
This is in the Moodle. I got this from Moodle. Jump and link. Jump register. So let's look at jump register. It's the RS, yes. The 8 is here, the 0 is here, and it's the first place. And what does this say? It says 0. All this is 0. To execute a branch, it's really a branch to an instruction. You see, you don't need to, all right, I want to explain something. Well, we talked about calculating the jump address and the branch and the thing. That was when we had an immediate value. When we had a regular jump command, we had an immediate value, for example, here, wait a second. Here's a regular jump. We have an index, we have an immediate value. You're seeing my screen, right?
Yeah.
Yeah. So here we have an immediate value, but it's only 26 bits. So we had to figure out a way to convert that into 32 bits. So we said take something from the PC, add 2 zeros to the right, and magic, you have 32 bits, and you know where to go. Because you need it, this is only 26 bits, you need to have 32. That was for a jump command of type jump, of type J. Now we're in a jump register, and guess what? At this register, RS, this is 5 bits. This is not the place to jump to, but this tells you what register to look in. Now, if I go and look in that register, how many bits am I going to see in that register? 32. It's a normal register. So that means I've got a complete address already there in that register. So I don't need to compute anything. I just jump to that's my PC. I just take whatever is in that register, and that's my PC. That's the next place I go to. So there's no computations going on in this command. I don't need
But
to
it says-
calculate.
Could you explain that again? We're going to that register, which is our register.
This RS is a register. It's one of the 32 registers that the MIPS comes with. Each register is 32 bits long. So when I say jump to this register, what I mean is jump to the address that's stored in that register. That means sometime previously in my code, in my program, the programmer, or me, I put into that register, whatever register I put there, let's say it's register 7. So in register 7, I put in a bunch of ones and zeros. What ones and zeros? The ones and zeros that specify the line of code that I want to jump to. So I've already created the full address. I don't need to hobble together bits and pieces to make the address. I have the address already in that register somehow. You know, in my code, I previously put it in. And now all I'm saying in this jump command is jump to that location as specified in that register. And since
Okay,
that
but
register,
that register, we said
Yeah.
that register 0 always has to be 0, right?
no, what are you talking about?
I thought, wasn't there a special register called 0?
Yeah, but I didn't write 0 here, did I?
No, but in the problem that we were doing.
Oh, if I would say jump, if I would write all zeros here, then I'm saying, I'm specifying register 0, which is always 0, and then I'm saying jump to location 0. That's all.
And
if this
Which
line
is where
so-
we already are.
And if this line is on line 0, then I'm jumping to myself. And then I can read that line and I execute that line again and I jump to myself again. And it'll be an infinite loop.
That jump is the offset, right? It's not the absolute
No,
address.
that register you mean?
Yeah. That register is telling you the offset.
No. That
No,
register
yes,
is
but-
telling you the absolute address.
Oh.
That's what I'm saying. That register, but 0 is not the address. It's not that I'm
Why-
jumping to, it's not that I'm jumping to address 0. I'm
you
jumping to
can't
the
do that.
address that is stored in register 0. Well, we happen to
Oh.
know from previous knowledge that register 0 always has the value 0 in it. So if I'm saying jump to register 0, then I'm jumping to line 0 because the
Which you can't
contents
do.
of register 0 is 0. You can do it. You can do it. It's just going to be an infinite loop.
But what's at line 0?
Oh, what's at line 0? So you don't remember, but in the question, it was written, which of the following commands which are stored in address 0?
Oh. I thought in general things aren't stored at 0. Didn't you say they started from like 400,000 or something?
That's
like
right.
that?
That's right. But this
But
in
this
this
homework
question,
is wrong.
Okay.
in this question,
fine.
he's not
In this
assuming.
hypothetical thing.
This is a hypothetical thing, and he's saying these lines are in line 0, and we're at line 0, and we're executing line 0. And this
Okay.
command is saying jump to register 0, and register 0 has in it the value 0, so therefore it's jumping to this line, so therefore it's an infinite loop. Now, exactly how to answer this question, I would just write for 3. This is an infinite. This line will, not change any registers, and will just jump to itself over and over again.
And could you? Yeah.
I mean, you could argue this question because you could say, well, wait a second. Actually, register 0 theoretically could have a value in it. In the simulator, it's always 0, but and by convention, all programmers never put anything there. But on a purely theoretical level, you could put a value there, and therefore, you could argue that it might do something depending on what value is in register 0. But that's
Could you
not
go
what he's
back to the jump register, like the breakdown of the command again for a second?
Yeah, again, this was from Moodle. I went to Kudot. I mean, you guys, it's all in English, but hopefully
Kudot
you know
assembler.
Kudot assembler means assembler instructions. And in here, we have this little folder, and he has 2 files, and one is this taxir, and then this one is like the official MIPS instruction set. That's like published. You can find that anywhere on the internet. It's not,
Okay.
but here it is.
And no,
And you wanted something
question
else.
was-
Wait, you wanted.
I just wanted
you
to
wanted
see
something.
the
Was
jump register again.
you wanted this,
Yeah,
right?
over here. What is it always 0 between bit 6 and bit 20? Like we don't look at those?
Yeah, he wrote 0 there in the official, this is like the official document, because it should be 0.
But it
It can be
doesn't matter.
ignored.
But it's going to be ignored anyway, because it's irrelevant. Like, I don't care. All I
So-
care, once I've seen that this, and I know what command it is, and all I'm interested in is where to jump to. What do I
So
care
the
about?
the 0 in the beginning from 26 to
It
31
really,
tells
the
you.
0 should really be, this 0 here should be not care.
Uh-huh. But the other 0 between 26 and 31 tells you look at 0 through 5. What does that tell you?
Oh, yes, this 0, remember, all archetypes start with 0. And when you see
And
a
that
0
tells
in
you
the
to look at the
archetype,
first 5 bits.
it means jump over to here and discover what command it is.
Okay, and
function.
this says 8, so it tells you it's a jump register. And then it looks at 21 through 25 to see which register.
Yes, which register
Okay.
has the address that I want to jump to.
Okay, thanks.
Actually, the jump register is going to be in homework in the next homework assignment too, so it's important to understand how it works.
Oh, goody.
But it's pretty simple. In other words, we don't really explain it because it's not complicated. We explain the jump and we explain the BEQ because you have to calculate addresses. Here, it's very simple. You just jump to whatever location is stored there. Okay, I don't want to do all the homework, but I'm glad that you're struggling with it because that means you realize, you may have to, that means you have to go back and review what we did and
Any
review
chance
my
we get
slides.
an extension on that?
We could get an extension on it.
Because it's just like it's tomorrow and like we're working on it, but like it will probably take time, and it's also not the only homework we have.
Not the only homework you have. I thought I'm the only course
No.
you're taking.
No, I wish.
You wish. You would learn it better, maybe. Okay, not that I'm saying you're not learning it, but where did I want to do now? I want to continue with my slides. Yeah.
Wait, when are we able to get an extension till?
When you look at the box, don't you see a date there?
No, we know when it's due. I think now it's due tomorrow night.
Yeah, because you can see that. So I'll change the date there. I don't know. I'll give you
Okay, then.
another. I'll give you another 3 days, something like that.
Okay, thank you.
Okay. So let's use our remaining time together to continue our studies.
And how much
Where-
more time is that now?
Well, I would like to go till 1, actually.
Till 1. Okay.
An hour and
Could
a
I
half.
just ask a quick
Yeah.
more like housekeeping question? Why we're doing this now at 11:30?
Well, first of all, it's kind of dumb to do it right before the other class. As long as we're doing it, unless, I guess you guys have other, I don't know, you have other plans. I actually have a doctor's appointment today, so I would have had to cancel class today if it had been a regular situation. So it's not necessarily always like this. Although,
fine. I just want to know, like, in
although for me it is a
general.
convenient time.
So actually, our Wednesday class is actually later, not at 1:30. Our Thursday class is at 1:30. Our Wednesday class is actually at 6.
At 6. So again, this is, well, we could have another class today at 6 if you want.
Instead of 1:30 tomorrow?
Instead of instead of 1:30. Is that acceptable?
Works for me.
This was kind of a one-time, I guess this is a one-time, although I did make this a recurring link, but what about this time? It's not a good time for you guys?
Not great for me. I don't know about other people.
Uh-huh.
Yeah, not
For
so
me,
great.
it's normal.
Uh-huh.
Me, it's fine.
Okay, well, if a few people find
Sometimes
it,
it's also fine.
so it sounds like a few people say it's not so great, so we'll do a different time. Does anybody remember where we ended last lecture? Had we started this section? Nobody remembers. Second. Since I put, by the way, the lecture. I hope you don't mind. I put it up here. We did the ALU, we did the RF, and the implementation of the add and the load word commands. Tov.
That's all in the book, right? Are we going in the order of the book?
Which book?
Um,
The book Patterson and Hennessy?
yeah.
Maybe. I'm not sure. I think it's very similar, but I don't know. It's exactly the same. So anyway, we did ALU, RF, add, and load word. Let me find that in my can't. So wait, we didn't do the branch. We do the branch?
Yeah, I believe we actually did the branch. I think we might have
We did the
finished
branch. Okay, great. So then we're on the next section. That's good. So here we are, single cycle. And so general notes. The diagrams in this chapter are simplified. In chapter 6, we will see fuller diagrams. For now, we keep them simple so that we can understand them more easily. In chapter 3, we explained that, in other words, we're going to show you, whatever, it's going to be simplified. For now, in chapter 3, we explained the structures of various components that we will use now as complete units, black boxes. In other words, the things that we already discussed before, we're going to view our components in this picture, and we're not going to explain the inner workings of them anymore because you already saw that. Examples of the components we use are going to be the RF, the instruction memory, the RF we know, right? The register file, the instruction memory, we know the memory, the data memory, just another memory. ALU we know, the sign extend. We never explained the sign extend, but we're going to use it. We're going to use it. There's also a shift 2 thing that does a shift 2, a decoder, and a multiplexer. Other components which we have not explained, but which are going to appear here, are the main control and the ALU control. So we're going to actually talk about the controllers now, which is important. So single cycle. In all MIPS setup, single cycle, multi-cycle, or pipeline, we can use each component only once per cycle. All right, that's a very important rule. Think about that. It means that what does it mean? In any cycle, I can only use a component once. Because what does a cycle mean? A cycle means at the beginning of the cycle, I put in the data I want, and at the end of the cycle, I get out the result. So if I use the component twice, then, but I only read it at the end of the cycle. So the first time I use it, I'm going to lose that data. So there's no point, I can't use it. In other words, I could use it, but it won't do anything. I only get the result at the end of the cycle. I only look at the result at the end of the cycle. So I can only use each component once. So if I need to do 2 additions, for example, and I have an ALU, I'm going to need to have another ALU. I can't do 2 additions with my ALU component in one cycle because I put the numbers in at the beginning of the cycle, and at the end of the cycle, I get out the answer. But if I want to do 2 computations, I need another cycle to do that. So if I want to do 2 computations in one cycle, I'm going to need physically 2 ALUs. Is that clear? Question?
It's clear.
Clear. Good.
What are all of those different setups, or should we not know that by now? The cycle, multi-pipeline?
We don't have to know it. For right now, all we're discussing everything is single cycle. Later, we'll discuss multi-cycle. We're not going to discuss pipeline. So you don't have to know that.
Wait, what are we saying a component is? A component is like the register number or the opcode?
No. We're finished talking about the structure of the commands. No, components are physical components of the computer. We just listed them in the previous slide. The RF, the instruction memory, The data memory, the ALU, the shift to, all those things are physical things we discussed in the previous chapters. You know, how do you build the RF? We discussed that for a long time. You remember?
Yeah.
So those are the components. I'm just saying, and so those components, we can only use the RF once per cycle.
Components are kind of like our tool belt kind of in any cycle.
They're like the bricks that are going to be used to build our building. We're building this computer, and we have different kinds of bricks. We have, I don't know, cinder blocks and bricks and glass windows and different things, and we put them all together and we get what we want. So those are the components of building, the physical components of the computer. That's why the course is computer architecture. It's the actual pieces, that building blocks that make the computer. And they're different types. We can use multiple. We can have 3 ALUs. We can have 4 ALUs. We can have 3 register files. We can have as many as we want, but they cost money. And we don't need more. We only need 1 register file. We might need more ALUs. In the single cycle, all the operations necessary to complete the instruction must occur in 1 clock cycle. In the single cycle, all the operations necessary to complete the instruction must occur. Well, that makes sense. That's the whole idea of single cycle. If it will be multi-cycle, we could use several cycles to get our result. Because of this, we must have separate data memory unit and instruction memory unit. In other words, we're going to, in 1 cycle, we're going to need to read the instruction, the command that he wants to do, and we're also going to have to read some data that he wants to get from the thing, if it's a load word or a store word. Let's say if it's right, we're going to have to read some data or write some data. But we need to do them both in 1 cycle, so we're going to need to have separate equipment to access the data memory and a separate equipment to access the instruction memory. Because we can't use the same equipment twice in any 1 cycle. And since everything's inefficient in 1 cycle, we have to have a separate door, a separate entrance to the data memory and a separate entrance to the instruction memory. Even though it's all there's 4 gigabytes of memory, but we're gonna have a special entrance to the instruction memory, which starts at place, we said 400,000. At a separate entrance to the data memory, which starts at place 10 million. Similarly, we need to have...
Those are kind of like pointers? Or like, what are those?
No, these are physical things. We're going to need to have a data memory unit. When I use the word unit, I mean like the carburetor unit of your car. It's like we're going to have 2 carburetors.
It's a piece of hardware kind of like plugged into the memory at a certain location.
Very well said, yes. It's a piece of hardware plugged into the memory that has the ability to read certain section of the memory. Only a certain section of it.
And it can like read forwards and backwards and do all these kinds of things.
Yes, it can read any place. It doesn't, it's random access. That's why it's not forward and backward. It's just, it can choose it. I can give it any particular location and it, boom, it goes and gives me that. Because we often need to access both memories, i.e. because we need to access both memories, yet we can only use each component once per cycle, but we're going to often need to do both. Similarly, we need to have an add unit in addition to the ALU unit. In other words, we have that big ALU which does add and also does OR and also does AND, but we're also going to need another thing, just an add unit, which is another component which will just do adding for us. So let's look at the picture. Before we get into the details of this operation, let's look and see if we're right. Look, it says ALU here. See that? I need some yeses.
We can see it.
Yeah. And you see the add? Yeah, so we have an add and we have an ALU. Here's our remember we saw this before. This is the RF, the register file. We saw before that the output goes to the ALU, and then that output can go to the memory in order to read from the memory or write to the memory. But now we've given us more complete picture. Here's another add. Here's a mutex, a multiplexer, and a multiplexer, and another multiplexer, another multiplexer, the sign extender we saw before, and the multiplexer. Now, I don't expect you to understand exactly why all these things are here, but as we go through various commands, you'll see how each of these components is used, and then you'll understand why we had to add them. In other words, if I only am interested in doing, I don't know, adding two numbers together, then I'm going to need a lot less components here. But because I have other things I want to do, I have to have more components. And every time I want to add a new functionality, that I have to check, are the components that I have here sufficient to achieve what I want, or do I need to add another component? Now, the main new thing that we see here is in blue here. This is the controller. This is what tells for example, remember we talked about like the mutex? It has to decide whether to take, it has to decide what value to pass to the ALU. You can either pass whatever came out of read data to, or it can pass whatever came out of the assign extender over here. Remember we talked about that. If it's a branch, it's going to need to take whatever came out of the assign extender. If it's I don't know, some other command. If it's a add command, it's going to take what's come out of the read to. Then it's going to. So we have to decide based on what command it is. We decide whether the mutex should send this data out or this data out. Well, who tells it? Who makes that decision? This line makes that decision. Where does this line come from? It comes from the controller. So if you're in a science fiction movie, that's like the all-controlling eye or something. He tells you, oh, this is a branch. I need that sign extended 16-bit thing. So that's what's going to come out of here. How does he know what to do? Well, look what it says here. Instruction goes in. What instruction goes in? From the instruction, which is stored in this instruction. Oh, this is actually instruction memory, but this is a simplified picture. There's actually a register here in the middle, but note this is instruction memory. Remember we said there's two units? This is the instruction memory unit, and this is the data memory unit. Both of them are directly connected to the 4 gigabytes of RAM memory. But this reads the instructions. And this reads or writes to the data. They're both connected to the same general memory. Now, he got the instruction out, and all those bits of the 32 bits of the instruction, some of them go, look, it says 25 to 21 go here, 20 to 16 go here, different ones. But in any case, the 26 to 31 goes into the controller. What is the 26 to the 31? What are those bits? Here I really need you to answer.
It's like a register that we're operating on, right?
No. On an instruction, what is stored in this is the leftmost, 31 is the leftmost bit. And 31 to 36 to 26 is the 6 leftmost bits. Right? 26. What?
That's the
opcode?
the command.
That's the
corresponding
opcode. That's the word I'm looking
Opcode.
for. That's the opcode. The command, that is the opcode. So in other words, Control Z. That means that if the command was, let's say, opcode 23 or 34, then the number 34 is going in here. You guys, I just got a message.
What about when it's 0?
Then 0 goes in there.
No, but then it needs to look at the end of the instruction.
Then it needs to get. Then you're interested in like where bits 0 to 5 are.
Yeah.
So look here. See, it says instruction 0 to 5.
Yeah.
they go into the ALU controller. Now, wait a second. Why didn't this controller do it? Think about it. If it's an R type, all the R types are basically adds and subtracts. So who's deciding what to do? The ALU. The ALU needs to know, should I do add or subtract? So we have a special little controller here just for the ALU to tell him what to do based on on which R type it is. You understand? So it's true, this controller, he's just going to see that it's 0. And then he's going to do whatever he's supposed to do on these lines for 0. And they're all the same. Doesn't matter what the instruction was. He's going to put out, as long as it's an R type, he's going to put out the same signals on these things. And where are we going to see the differentiation? Only when these 5 bits come into this ALU control, only in the ALU.
So what's the difference between the regular control and the ALU control?
Well, the ALU controller, as you see, just controls the ALU. Whereas this controller has lines going into this mutex, lines going into the data memory, lines going, has many more lines coming out of it, controlling many more things.
So why don't we just have the regular control? Why do we also have the ALU control?
Well, because if it's an R type, we need to have the 0.5. Then we need to have the 0.5 also going into the controller. And we'd have to build a bigger controller. You'd have to accept not just 6 bits, but 11 bits. And then it'd have more lines coming out. And since in most cases, they decided it's just more efficient to have a separate small controller in the case that it's an R type. And here, everything, basically what we're saying is, we took this functionality out of the controller and stuck it over here. It's what?
What's the 0 to 5 again? What's the 0 to 5 again?
If it's an R type, the 0 to 5 is the function. That's what tells us of the R types what to actually do. And the only differentiation in the various R types, according to this diagram, is what the ALU does. In other words, if it's an add or a subtract, as far as the controller is concerned, it's the same thing. He's going to do the same behavior. But if it's add or subtract, we need to tell the ALU what to do. Are you doing subtract? Are you doing add? So, you see what I'm saying? So the reason, that's why we separated out. In other words, if we had wanted to do, we could have done it differently. We could have said that the opcode, instead of being 6 bits, is 8 bits long. And then we would have stuck 8 lines into the controller, and then the controller would control the ALU. But remember, we decided that we want to keep the opcode small so that we can expand the immediate space. So only in the R type do we want to have those extra bits to tell us what to do. So we kept the controller small, we kept the opcode small, and only in the case that it's an R type do we have those extra bits coming into the ALU controller telling you what to do. You're asking questions like, why is it like this? It could have been different. But there are efficiency reasons why it's like this. But for now, I think that's more important than understanding why it's like this is just to understand how it works. Like, once you understood how it works, then we should ask this question. Why did they do it this way? They obviously could have done it other ways. What's the advantage and disadvantage? But first we have to understand first we have to agree that it could work, that working this way will work, that doing it this way will work. There are other ways to do it, but this way will work, and we're going to investigate exactly how it works for each command. You guys agree with me?
Yeah, good point.
Yeah, okay. So central controller. The controller receives 6 bits of input. We saw that, i.e. the opcode of the command, bits 26 to 31. We saw that. Based on these inputs, its logic gates produce various outputs and control lines that come out. Well, that's what we saw. In other words, it has an inner working that we're viewing as a black box at the moment that controls the whole chip. The following slide shows 4 examples. The following slide, or slides, I don't know. The following slide shows 4 examples of what output will occur for different opcodes. set the lines for LW and see if it works. So it does. So the following slide shows 4. So what we're saying is that if the command, let's before I go on, I mean, let's first step is to understand this diagram. And what it's saying is, assuming the instruction is LW, we're not doing all the instructions here, but assuming the instruction is R format, just a second, I'm going to tell my. Hello? I'm back. Hello? Give me is anybody there?
Yeah, we can hear you.
You're all there.
Okay, great. Wait, let me go like this. Yeah, I don't see any videos of you guys. So we have grouped together the R format, and then we have the LW, the load word, the store word, and the branch equal. Those are pretty much what we've been discussing all along. So those are, we're going to continue discussing those. And what we're saying here is that these ones and zeros are the values that are going to come out on the control lines of that controller. So let's go back to the picture. See this control line? It has a line, for example, branch. It's labeled branch. Another line that's labeled, for example, memory read. So let's go back to this picture. So memory read, if it's an R type, will have the value 0. Branch, if it's an R type, will have the value 0. Notice that branch is 0 for all 3 except for the BEQ. Well, that makes sense. Branch is basically saying, is this a branch command or not? That's why it's called branch. In other words, whenever branch is 1, it's because it's a branch command. If it would be a BNE, there would also be a 1 here. Now, what else? Here, a load word has a lot of 1s over here. Now, there's the ALU source is 1 for a load word and for a store word. So what I said over here is, let's take the LW and see if these signals, no, this is the job, if these signals work. But basically what this chart tells me is, what is the job of the controller? What should the controller do when it gets this command or this command or this command or this command? If it gets an R format, it should light up these bits. It should light up the register destination, the register write, the ALU op1. Those are the bits it should light up. Now, if you notice over here, yeah, question?
Sorry, can I ask a question? R format, it's supposed to get all zeros as an op command, right? Or am I wrong here?
Yes, we're not discussing the input. The input, if it's a, yeah, if in order for it to be an R format, that means that it got as an opcode all zeros. True. And on its output
and then
lines,
the outcome should be the
output line should be 100100010. Exactly.
And we'll see later in the black box how that comes out.
Yeah, well, I don't remember if we discussed that at all. But I think so, yes. I think like in chapter 10 or something. We're not going to get to it for a while.
Okay.
But now look over here, the ALU op. This is ALU op 1 and ALU op 0 and 1. So what it says here is ALU op 2 bits. In other words, we can view this ALU op as 1 2-bit field because they both go to the ALU. And op means operation. What operation should the ALU do? And you see that if it's 0 0, like here, then it should do add. If it's 0 0 like here, then it should do add. If it's 0 1, notice it's 0 to 1. So it's 0 1, then it's subtract. Oh, no, I read that wrong. If it's 1, I'm sorry, I switched it around. It should be in the order that's here. If it's 1 0, if it's 1 0, it should be R type. Well, that makes sense. It's R type. If it's 0 1, it should be subtract. That's here, BEQ. Right? 1, 0 is R type. So this is this is the meaning that the ALU will understand if it's based on these bits. It will understand add, subtract, or R type.
When it's 1, 0 R type, what like that means that the ALU isn't being used, or like what does that mean?
That means that the ALU, so go back to the picture, that means that the ALU is going to be controlled by the ALU controller instead of the, see here. What was the ALU? The ALU op, here's the line. This, it's this black line. You see this ALU op? It's this dark line here. It goes into here. Now, basically it's like this. If it's R type, which what do we say? It was 0, 0. R type is no 1, 0. So if it's a 1, 0 on this line coming into the ALU controller, then the ALU controller says, oh, it's 1, 0. That means I better look at what's coming in on these 5 bits, these 6 bits. And that will tell me what to do. If it's not 1, 0 over here, then it's either add or subtract. So basically, this ALU controller is very smart. He basically said, if I put 1, 0 on this line, it's telling the ALU controller to ignore the input, to relate to this input and ignore and don't do anything based on this input. But if it's not 1, 0, if it's 0, 1, then it says, then the ALU controller ignores these lines and just sends a subtract command to this guy. You see what I'm saying? If it's a 1, 0, then the ALU will decide what to do, what to tell him based on these inputs. But if it's not 1, 0, then he's going to ignore these inputs because it's not an R type. If it's not an R type, then these inputs are irrelevant. It's true they're coming in.
If it's not
totally,
an R type,
yeah,
then what is the ALU doing? Like, isn't
oh, because the ALU sometimes does other things. If it's a branch, we learned. If it's a branch command, he may have to compute the branch address. And in order to compute the branch address, he may have to add things together. So the ALU is working. But he's not adding to registers. He's adding an immediate. And, he's doing an add I, for example, is not a R type. But the ALU is for sure going to work. True?
yeah, okay.
So in other words, if it's an R type, then this command, then this line will tell him what to do. If it's not an R type, it's an I type, then he's going to ignore these lines and he's going to decide himself what to do based on this input line. It's complicated. These are engineers that figured out ways of doing things in the most efficient way. Instead of just having, 7, obviously they could have had 7 lines, coming out into this ALU controller. And then all the time, but they said like this, a lot of those times those lines will be irrelevant. So instead of sending a lot of zeros, they just sent 2 lines over here. And they said, if it's this or this, if it's this or this, then you're done. And if it's not this or this, then you got to look at these other 6 lines. Again, we're trying to get as much flexibility with as little components as possible. That's the goal. The goal is, if you think about it, we're engineers. We're trying to get as much use out of the components that we have without adding all kinds of extraneous components. So they figured out clever little tricks, and that's what we're learning. We're learning these clever tricks. And the trick is that we're keeping the controller small here, and in many of the cases, we'll have enough information to tell ALU what to do. And only if it's an R type do we need extra information. And then we use this other piece. This is what it is to be an engineer. So we understand it. So, oh, here's actually I haven't looked at these slides in a while, and actually we do explain the controller right away. But what I really want to do on the board, I mean, I don't have a board here, but what I want to do is take the LW and run it out and see if it works. So let's see if, how can I do that?
There, I think there's an annotate function thing part of Zoom. I don't know where it is.
Annotate.
No, in Zoom, not in
Yeah,
Google.
I understand. Annotate. Yeah, I see it. Let's see. Let me go. Let me do something quickly. Writing. I normally be on the whiteboard and I'd be writing in the numbers on the lines and showing it to you. But let me just do it like this. Like LW is you should probably write these numbers down. Write down copy down this table for yourselves, or at least the line for the LW. And all you have to really write is that the ALU source is 1, that the memory to register is 1. Let's write down the ones. The register write is 1, and the register and the memory read is 1, and everything else is 0. So now we can go back here and we can look at this. Say, where's the memory read? So the memory read is this line, and he is 1. Let's think about that. Why is the memory read 1? Because this is a load word, right? We're talking about a load word. What do we want to do in a load word? Well, the fundamental thing we want to do in a load word is read the data. We want to read the data and load it into a register. So we have to put a 1 here. This is the read line. This is the write line. We're not writing to the data, we're reading. So therefore, that's why the memory write was 0. Right? If you look here, the memory write was 0. On a store word, the memory write is 1, and this one is 0. Does that make sense?
Yes.
Somebody? That makes sense?
What about the
Yeah,
the other
makes
ones
sense.
there? Like reg write and mem2 reg. And
Well, I'm doing one by one. I'm doing one by one. We're going to do it one by one. First step, I'm taking baby steps because I don't want to lose anybody. So just repeat. The memory read, if it's a load word, obviously I got to read for the memory. So I'm going to, this bit we learned, when we learned about the data memory, we learned that this line is the read line. And it can only be, if this is 0, this is 1, this has to be 0. And if this is 0, this is 1, this has to be 0. So we're reading, not writing. So we have to light this up and say, give me some data out here. Okay, let's check another number. Well, register write has to be 1, according to what we saw before. I copied it down. I can go to present. Let me go to view, present. Okay, so right now, let's I do mark. Let's see if I do annotate. And what does it do? Draw. I do a draw, and I do like, we did memory read. And I draw 1 here. Yeah. Oh, great. You see that?
Yeah.
So I put a 1 on memory read. Where else am I going to put a 1? On register write. Register write here. So let's put a 1 here. And where else am I put a memory to register? Memory to register. So let's put a 1 here.
Wait, what's the difference between the mem to reg and the mem read?
We're going to find out. Don't worry. We're going to find out. Here, let's put this 1 also here. Right? I'm just carrying on the 1 down to there. So remember where it's going. And that's the memory to read. And now ALU source is 1 also. ALU source is here, 1. Every other line is 0, and zeros are harder to draw, so I'm not going to draw them. But every other line is 0. So let's go. Now I can get rid of this annotate. No, sorry. Okay, so now, Yofi, our instruction comes in. It's a load word. Now, what type is load word?
Archetype.
No.
Pseudo.
What? What type is a load word?
Okay, doesn't it have to be an R type?
No, it's not an R type. How many registers in a load word? 2.
Oh, so it's an I.
This all R type always has 3 registers. So this is got to be an I type. It's an immediate. I've got 2 registers and an offset. The offset is my immediate in this case. The offset is a 16-bit immediate. True? True. So what's going to happen? The opcode is going to go into the controller, and that we don't care about. The controller is going to do its magic, and 1 and 1 and 1, and this one are going to come out. So we've thought about the 1. Now we've got to think about the other 3 fields. We've got the 16 bits. So I look quickly here and I see 16 bits. No, I don't see 16 bits. I look here and I see 16 bits. That's the 16 bits that I want from the instruction. Ooh. That's the 16 bits that I want from the instruction. And those are telling me the offset that I need to add to the value in the register. Okay, now where are those 16 bits going? First of all, they're going to this. No, what? I hate that. Anyone know how to get rid of, every time I put my mouse near the bottom of the screen, I get this pop-up of telling me, do you want to exit? Anyway, it goes, anytime I move the mouse, it tells me I like to move the mouse. Okay.
You might be able to drag it away. That would be the hope.
Drag it away. No, I can't drag it away. If I take exit, then it's going to just exit the whole view. So I'm just going to, it goes away if I just don't move the mouse. So, but I like to move the mouse. Or maybe I do annotate. Let me do annotate.
Or click on the pointer button and on the pop-up.
Oh yeah, pointer.
That might help.
Ah, okay. And now wait for it to go away. It's not going away. But then I move it, it does the same thing.
Okay.
Doesn't seem to help. Let's get rid of the pointer. Let's try annotate. Ah, yeah, annotate is good. So here, so the instruction comes down, and these 16 bits come through here, and they go through the sign extender, and they come out as 32 bits, and they go up, 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 and they go here into this mux. And look at that 1 that I wrote above that mux. What is that 1? That's the one that the controller put there. That tells him to take that data that just came through and keep going with it. Everyone agrees?
Yeah.
Right? That's why that 1 was there, so that this could go through. So now we've got the 16 bits taken care of. We have still to think about bits number 25 to 21, because that's the opcode. What about bits 25? That's from the instruction, that's coming in, and that's the read register. Right? That's what it means. That's the read register, and that means it comes in and comes out here 32 bits. 32, can I write it? 32. 32 bits come out here, and 32 bits come out here, and I add them together, and lo and behold, I have computed the address that I want to read. And fortunately for me, there's a 1 on this line, and this 1, ooh, I lost my writing. I'm having fun here with no, right. And now this 1 here comes in, and he tells me I want to read, not write. So what comes out here? How many bits come out here? Hello? Somebody got to know. How many bits come out of here? A 32-bit, 32. A 32-bit address came in, and a 32-bit value came out here. This is the value at that memory location, because this is a load word. I need the value at that word space. Well, I just got it. Now, this mux, in order for this value to continue on its path, remember we're describing now the data path. In order for this 32 bits to continue on its path, we need to have a 1 on this multiplexer. Because otherwise the 0 will come out here. Otherwise, whatever coming from this line, well, we don't care what's coming out of this line at the moment. We want this line. So we need a 1 here. And lo and behold, the controller is very smart. He put a 1 on this line. So that means that the 32 bits out of here, no, I lost my writing. Draw. The 32 bits will come out here, go down, and you can't see it at the bottom of the screen, but it's going up, down here, up here, and into here. And that's just where we want it to go, because that is the register file, and we need to write that data into the register. It's a load word. Well, which register? Well, just so happens that we know which register. It's the register at instruction space 20 to 16. That was the one that told us where to read from. This is where to write to. Question, yeah.
If this is single cycle, we can only use all the components once. So we already used the component to read. How can we go back and use it again to write?
I love that question because I have a great answer. The best questions are the ones you have a great answer for. You're saying, how can we read? And we already read from this, and we said we can only do everything once per cycle. How can we also write? So if you remember when we discussed the register file, we specifically noted that the register file can simultaneously read and write. He can do 2 things at once. In other words, we can't read and write, but the register file is capable of simultaneously doing a read and a write. As opposed to the ALU, the ALU can do 1 add or 1 subtract, or we can't do 2 adds, but the register file is specifically built so that it can simultaneously do 2 actions. Does that answer your question?
So, yeah, so pretty much it's like you're half using it for the first part when you're reading from it, and then when you come back to it, you're using the rest of it pretty much as it's one use.
Yes, you could say it like that. But I would say it even more meduyak, and more exact, and I would say it's simultaneous. In other words, it's not that first and then later. This is all happening in one cycle. So that means even though I'm describing it sequentially, you have to imagine it as boom, all this happened. In other words, it's simultaneous.
So the latency is negligible?
Exactly. The latency is the latency of the time of a clock cycle, which is if it's a 4 giga, it's like a 2 gigahertz computer, it's, a half a billionth of a second. In other words, there is a latency, but basically by the end of that 1/2 billionth of a second, everything happened. And from my perspective, it's like I did a stamp. I just went boom, and all the stuff happened. So it's not really like it first did that and then that. It did all simultaneously. But we have to think about it sequentially because you have to say, well, what date is it writing here? It had to be after this happened. So it's a little bit confusing, but the way that you can think about it sequentially, it's slowly happening in the course of that 1/2 billionth of a second.
Okay, thank you.
And by the end of the 1/2 billionth of a second, it has read and written. And that's what the register file can do.
How does it
So-
know where to write to?
Oh, so that's what I was just about to say. That's where the question stopped me. Now,
All right.
we already said, so that's a great question because it gets me back on course. 25 to 21, we said is where to read from. And we said 15 to 0 is the offset that we finally extended and put through here. So all that we're left with is from 16 to 20. Well, that is the register to write to. And that went into 2 places. Look at that. 20 to 16 goes here, but it also goes to here. So now all we have to do is make sure that these 20 to 16 get into this mutex, and this mutex puts it into this write. Well, that means that this mutex controller needs to have what value on it? This line should have what value on it?
A 1.
Wrong. Try again.
0.
Yeah. It needs to have a 0 on it. This line needs to have a 0 on it because, after all, this says 0 here. This says 1 here.
Oh, I see. Okay.
So the 0 here means that this line will be continued on. So I want this to continue down here and in here. So I need a 0 on this line. Well, we didn't write anything on this line. Well, if we didn't write anything on this line, that means it was a 0. We only wrote the 1s. So if we want, we could write a 0 here, but there's a 0 here. It's hard to write a 0. So there is a 0 on that line. So we explained why the 1 was here. We needed that. We explained why the 1 was here. What other ones did we have? We had this one. Well, we needed to, that was telling the register file to allow a write. Right? We had to have a 1 here to allow this write to occur.
Or else what would happen?
Or else
It would just
this
ignore it.
register would lock up and it would say, I'm sorry, I don't care what data is coming in, I'm not writing.
Mm-hmm.
The data would come in, but it just wouldn't get written. So that's it. We've explained now why there's a 1 here and a 1 here and a 1 here. Is there a 1 that I'm forgetting? I thought there were 4 1s. There are 4 1s. What about the ALU source? Why didn't I write that? ALU source.
We did that. We did it.
Oh, we did
We
that.
did write
I
it.
just didn't write it here. Here. So those are the 4. And here is the ALU source. And we explained that the 1 had to be there. So there you go. I think that's really good. I hope that that's very clear now. So we see, and we did, what do I do, escape? No. Now I have to go here. And now if I go, no. Here, annotate. Now, oh, I should, anyway, I should clean that up. But anyway, we've gone through the LW and shown how these bits are the right bits to light up on this controller for this diagram to produce the result that we want. I leave it to you. I'm going to stop now, but I leave it to you for in your own time. And I really, not homework, but I mean, it's homework that you don't have to hand in. I really think you should go through the at least, go through the other 3 commands that are here and prove to yourself that these 1s are the right ones to light up. When it's an X here, what it means is a don't care. Doesn't matter what's in there. But you can imagine a 0. So you should take this chart and take this diagram and show that the other commands work. And then you'll really be very well placed in your understanding of this material. In other words, that's a major topic, and I think the most important is to understand, to how to read this diagram and how these bits have to be lit up. Okay, so
Is
questions?
this usually how a system looks like, or can it look completely different as well?
Not sure I understand what you mean. In other words, every
As
system will
in,
have.
is this the basic thing we need to understand, or could it be that it looks different in any other computer?
No, every computer will have a controller. Every computer will have a reference. No, all the things all the components will be in all computers. The only difference is what the line, how many components there are, how big the instruction set is, how big obviously if it's a 64-bit instruction, then it's different. But the components are all going to be the same. They're all going to have a controller. The values on the lines will be different, right? On a different computer, you might have different lines and different values. In homework number 2, and then homework number 3 that you haven't yet been assigned, there's going to be, okay, now take this and add to it in order to do this new command. Or to do like JR. We didn't describe how a JR works, jump register. What line, how would a JR work on this? That would be, think about that. Do you need to add, is this diagram sufficient to have all the components to do a JR or not? And if so, what would be the control line? Which ones would be lit up? If it is sufficient, what would be the numbers on this? And if it's not sufficient, what would you have to add? But yes, every computer will have all these components. Some might have more multiplexers, some might have more ALUs. Any other questions? All right, so we'll stop here.